Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about multivariate discrete random variables. Our goal is to learn how to model interactions between multiple uncertain discrete quantities within the same probabilistic model. Up until now, we have learned how to deal with individual quantities. When these quantities were discrete, we have learned that we basically define their PMF and we can just work with that and model them as discrete random variables. Today we're going to see how to model several uncertain quantities as random variables jointly. The prerequisites for this material are probability and discrete random variables. Okay, so let's remind ourselves of how we defined random variables mathematically. Mathematically, random variables are functions from a sample space to, in this case, a discrete set, because we're going to be considering discrete quantities. And what was important is that the probability that the random variable is equal to, maybe I'll use this instead, the probability that the random variable is equal to each of its possible values, that needs to be well defined. And if you remember, for this to be well defined, you need to go back to the sample space and ensure that the corresponding events in the sample space were well defined. But as I have been reminding you over and over, we shouldn't worry too much about this mathematical formulation. At the end of the day, we're going to define these quantities directly. However, this mathematical formulation is important to understand how we model the interactions between random variables. Because thanks to this mathematical formulation that might seem a little bit complicated the first time you look at it, representing random variables as functions, this actually makes it very easy to model interactions. To see why, let's take a look at a very concrete example where we have two rolls of a die. We already talked about this example when we defined discrete random variables. So the idea is that we have a probability space that represents two rolls of a die, of a six-sided die. So each roll can have a result that is 1, 2, 3, 4, 5, or 6. And we represent the outcomes as a two-dimensional vector. Each entry represents the outcome of one of the rolls. So our sample space essentially has 36 points that correspond to the possible outcomes of the two rolls. Okay, so now we are interested in several quantities related to this uncertain phenomenon, and the way we define those quantities is as functions of the samples. So for example, we might be interested in the result of the first roll. That function is very easy. We just take the first entry in the vector. What about if we're interested in the result of the second roll? Then we take the second entry in the vector. What about if we're interested in the sum of the two rolls? Boom, the sum of the two entries, okay? I do want to remind you that we never actually in practice define random variables in this way. We just define them through the probability that they're equal to specific values directly. This is just a mathematical framework underlying their definition, but it's actually very important to look at the mathematical framework in order to understand how we're modeling interactions. Okay, so the important thing to remember here is that when we fix an outcome, when this omega is fixed, it fixes all of the random variables defined in that probability space at the same time. Okay, so for example, if I roll the two dice and the outcome is 3, 1, first roll is 3, the second roll is 1, then I'm fixing the value of all random variables related to that phenomenon simultaneously. So in this case, A is going to be equal to 3, B is going to be equal to 1, and C is going to be equal to 4. So then it makes sense for us to think of events such as, what is the probability that A is equal to 3 and at the same time C is equal to 4? What's the probability that B is smaller than 3 and at the same time A is greater than 4? And so on and so forth. Now it makes sense because the outcome in the probability space, the outcome that we choose in the sample space according to a probability measure fixes all random variables simultaneously. Okay, so this is a picture. Here we have two random variables, A and B. And what I'm showing you here is how we actually manipulate these random variables, which is through the probability that they're equal to particular values. So if we're interested in the probability that A is equal to 3, sorry for my handwriting, and B is equal to 1 at the same time, then if we're like thinking very mathematically, and in general when we're doing probabilistic modeling we're not going to do this, but it's important to do it now at the beginning to just understand that there's some underlying mathematical framework that actually makes sense. If we want to think about this event, we have to go back to the sample space and see, okay, what is the event that maps to 1? So B is a function that maps from the sample space to different values, and in particular that set maps to B of omega equal to 1. Okay, like all of the outcomes that map to 1 are within that circle. We also look at the values that map to A is equals 3. So A is another function from the sample space to different values, and these ones in particular map to A omega is equal to 3. But what we're really interested in are the values for which both of things happen. Both of these things happen, right? A is equal to 3 and B is equal to 1. So we have to go back to our sample space and look at the intersection between these two events, and that gives us the probability that A is equal to 3 and B is equal to 1. Why are these probabilities well defined? Well, they are well defined as long as the random variables are well defined, because if you remember the definition of random variables, which we mentioned a moment ago, means that, let me erase this so that you actually see something. It means that this event is well defined because it's the pre-image of a certain value of this random variable. So for the random variable to be well defined, that event needs to exist, it needs to be assigned a probability. And on the other hand, this other event here, that is that A is equal to 3, is the pre-image of this value, the fact that A of omega is equal to 3, that also needs to be in the collection of events that we consider in the probability space, because otherwise A would not be a valid random variable. And now we have the intersection of those two events, both of which are assigned a probability. And if you remember, in probability spaces, we always assign probabilities to the intersections of events that we are considering. So automatically, that event has an assigned probability. So the probability that A is equal to 3 and B is equal to 1 is well defined under our mathematical framework. That those probabilities are gathered into a function called the joint probability mass function. So the joint probability mass function of two random variables A and B tells us the probability that A is equal to each of its possible values, and simultaneously at the same time B is equal to each of its possible values. And this is really what we use to manipulate the two random variables. We forget about the underlying probability space. It's a valid probability space. There must be a probability measure that assigns the probabilities to the right events and so on. We basically don't bother with it. This is what we're going to estimate from data. Just in the same way as we did for a single discrete random variable, where we told this story about the underlying probability space and so on, but at the end of the day, what we do is we use the PMF, we estimate it from data, and that's what we actually use to compute probabilities that we're interested in. Okay, so a joint PMF of two random variables looks like this. These are the possible values of A, 1, 2, and 3. These are the possible values of B, and the height of these bars tells us the probabilities that, for example, A is equal to 1 and B is equal to 2. That's this big bar. So in this case, that's the probability is 0.4. The probability that A is equal to 2 2 and b is equal to 3 is this bar here, the probability is 0.05, and so on and so forth. Okay, so that's a joint PMF between two random variables. You can also define the joint PMF of 3, 4, or as many random variables as you want. Usually when we consider a lot of random variables, we call them a random vector, and we essentially put the random variables into a vector like that so that each entry is a random variable. It doesn't really matter very much whether you say that these are d random variables or a d random vector. It's just often more convenient to treat it like a vector. The joint PMF of the random vector is just the probability that the first entry is equal to some fixed value, the first entry of this fixed vector. The second entry is equal to some fixed value, up to like the dth entry is equal to that fixed value. So here notice that x is d-dimensional, and this x without a squiggly line, we're going to do just like normal variables with vectors. If there's no squiggly line on top, that's a fixed value. So here you can imagine that you have some vector that has some values like 1, 3, 4, and you're saying what's the probability that this vector is equal to this vector, which means that the first entry is equal to 1, the second entry is equal to 3, the third entry is equal to 4. Okay, so hopefully that makes sense. And the joint PMF tells you the probability that those entries are equal to those values at the same time. Okay, so the joint PMF, just like the PMF allows us to compute any probability that we actually care about for a random variable, the joint PMF allows us to compute any probability that we care about regarding two random variables at the same time. So here, when I say A and B belong to a certain set, what I mean by that is you're saying A is maybe between 1 and 10, and B is smaller than 3, and so on and so forth. So you can imagine, you know, the values of so if this is A and this is B, and maybe these are their possible values, what we're saying is, what is the probability that they are here? What are you going to do to compute that probability? So since the joint PMF, not these guys, the joint PMF captures the probability that you're equal to each point, what are you going to do? Well, probably you're going to look at the value of the joint PMF, and you're going to add the value of the joint PMF here, plus here, plus here, plus here, right? So let's actually show that that works out mathematically. We want the probability that A and B are in this set S. That's the union of the events that A is equal to a fixed value of A such that A and B is equal to S. Sorry, no, actually, to the event A is equal to this fixed value and B is equal to this fixed value at the same time, such that the pair of values is in the set that you were interested in. And you need to take the union of all those particular values of A and B that are in that set. Now is when we realize that these events are disjoint. Why? Because A and B cannot simultaneously be equal to 2, 3 and to 23, 4, right? Like they cannot be equal to two different pairs at the same time, because once we have an outcome in the sample space that fixes the value of A and B, so those sets are disjoint, we can add up their probabilities, and now the probabilities of these individual pairs, they're just the joint PMF by definition. Okay, so the joint PMF allows us to compute any possible probability that we're interested in regarding this pair of random variables by exactly the same argument. It's going to give us any probability that we care about for d random variables or a d-dimensional random vector. So the idea is exactly the same. You say, okay, what's the probability that the random vector is within this set? You look at the individual values that the vector takes to be in that set, and you add the joint PMF over them exactly like we do here. Okay, exactly the same idea. Let's look at an example. So now we're interested in the set A smaller, strictly smaller than 2. That includes, just here, maybe let's change the color, A equals 1, right? and b at the same time be greater than 1. So that's b equal to 2 and to 3. So which are the points that are in the set of interest? This one and this one, right? So it's going to be the probability of this, which is 0.4, plus the probability of this, which is 0.1, unless I've done something stupid, but I think that's true. So let's see. Yes. Okay. So here you see how the joint PMF allows us to compute any probability that we're interested in related to these two random variables. We don't need to think about the underlying probability space, but it's kind of neat that we have a mathematical framework that enables us to capture these interactions with this idea of representing the random variables as functions. Okay, so what are the properties of joint PMFs? We have defined the joint PMF as a probability. So in particular, it has to be non-negative. And another important property is that if we add all of these probabilities, all of these joint PMFs over all the possible values of A and B, so here big A is the range, this is the range of A, all the possible values that the random variable A can have, and B is the range of B. So when we add over all the possible values of A and B, what's going to happen? We're going to get the probability that A is equal to its range intersection B is in its range. But this always happens, right? Like this actually, if you realize, like the pre-image of all of these events is actually the original sample space. So the probability has to be 1. This means that joint PMFs always have to add up to 1 when you consider all the possible values of the random variables. By the same argument, if you add all the possible values of the entries of a random vector, you sum the joint PMF over all possible values of the entries of a random vector, then this is also going to be equal to 1. Okay. Any function with these properties is actually a valid joint PMF of some random variables or some random vectors. As in the case of random variables, the proof here would amount to constructing a probability space. And the way you would do it is you would just take directly every possible value would become an outcome. The collection of events would just be the power set of all those outcomes, and you would use the joint PMF to define the probability measure. Again, this is just a very technical term in case some of you are very mathematically oriented and are wondering, sure, great, like you told me about this underlying probability space, but now we're just working with joint PMFs. What happened to the probability space? What happens is that the probability space is a mathematical abstraction that makes sure that everything makes sense mathematically, but it really has no practical impact because we directly work with the joint PMF. I hope that makes sense. Okay, so we know now how to use joint PMFs to compute the probabilities that we're interested in, but what happens if we have some data? What do we do? Well, imagine that you're interested in modeling the joint behavior of two uncertain quantities. You look at some data and this is what the first quantity is equal to, and simultaneously this is what the second quantity is equal to. And the important thing here is that you get to observe data which ties them together, right? These two happened at the same time as the one. These two happened at the same time as the two. If you observe the two quantities separately, you cannot do this. You cannot model their interaction. Okay, and that's important to remember. Okay, so now if we see this data, what do we think the joint PMF at 2, 1 should equal? So what maybe you're going to do by common sense, and I recommend that you stop the video for a moment and you think about it, is you're going to see, okay, how many times am I seeing 2, 1? It's 2 times. What's the total number of data that I observe? It's 4. So it looks like half of the time I'm seeing 2, 1. The probability of 2, 1, which is the joint PMF at 2, 1, should be equal to 0.5. Okay. Actually, I didn't even write the solution there. It's 0.5. So in general, we again apply empirical probabilities. This is exactly what I was doing right now, right? To compute the joint PMF, just like we used empirical probabilities to approximate the PMF of a single quantity. So the idea is that if you want the joint PMF at a certain value, you check how many times that happens, right? This is an indicator variable that is equal to 1 every time a data point is equal to W, and you sum over all the data points. And then you have to normalize dividing by the number of points. It's essentially just the joint PMF is a probability. Let's use empirical probabilities to estimate the joint PMF. Okay, so let's take a look at an example with real-world data. This is data from the Movie Lens data set, which contains ratings given from users to movies. And what we want to do is we want to model the ratings given to Independence Day and Mission Impossible. We want to model these ratings jointly. So we need to consider users that have rated both movies. This is what I was referring to before, right? Because if I have a bunch of users that have rated only Independence Day and a bunch of users that have only rated Mission Impossible, then I'm not going to be able to model the joint interactions. Okay, so let's take a look at how this data look like. So this is the number of people, of users that gave a particular rating to both movies. So, for example, there were 20 users that gave Independence Day a 3. I'm very distracted because there's a truck down there. I'll check later if you can hear it in the microphone, but I'm getting very annoyed. But as I said before, it's New York City, so what can you do? Hopefully you're not hearing it too much. Anyways, the number of people that gave Independence Day a 3 and Mission Impossible a 4 is 20. The number of people that gave Independence Day a 2 and Mission Impossible a 1 is just 3, and so on and so forth. So how do we convert these ratings, these empirical counts of the ratings given to both movies, into a joint PMF? We just normalize it. That's all we need to do. So we divide by the total number of ratings, and that's how we get the empirical joint PMF. Here I've expressed it as a percentage. So here we see that about 13% of people gave a 4 to Independence Day and a 3 to Mission Impossible. Just 1.3% of the people gave a 3 to Independence Day and a 5 to Mission Impossible. I didn't mention this, but 5 is better. So if they liked it a lot, they will give it a 5. If they didn't like it at all, they will give it a 1. Oh, and now we can use this, by the way, to compute probabilities, right? Like, we want the probability that someone really didn't like Independence Day and Mission Impossible. We might define that as giving a 1 or 2 to Independence Day and a 1 or 2 to Mission Impossible. So then that would be 0.6 plus 1 plus 1 plus 3.8 would give us that probability. And we can compute any other probability with respect to these two movies in that way. Okay, so let's take a look at another data set, Precipitation in Oregon. I'm going to look at 3 weather stations that are situated in John Day, Corvallis, and Coos Bay. Okay? And we're going to be interested in when it rains. Not the amount of rain, but just whether it rains or not, because we're interested in discrete random variables. And we're going to model that with 0 and 1. So here, 0 means that it does not rain in Coos Bay. 1 means that it does rain. And now I got some hourly data that is online, and that tells us whether it was raining in those places or not at the same time. And again, this is very crucial. You need to get measurements that are taken at the same time in the 3 places. And here you can see the counts. These hourly measurements over a whole year. So this says that it was not raining in Coos Bay, it was not raining in Corvallis, it was not raining in John Day. We have 7,253 such measurements. Raining in Coos Bay, not raining in Corvallis, not raining in John Day, 462, and so on and so forth. How do we convert this into a joint PMF? This is a joint PMF of 3 random variables, or alternatively of a random vector with 3 entries. Well, we need to take all of these counts and normalize them so that we see the fraction of times that, for example, it was raining in Coos Bay, raining in Corvallis, and raining in John Day at the same time. Okay, we need to normalize that by dividing by the total number of measurements. And if we do that, we get this joint PMF, and we see that it was just 0.8% of the time that it was raining in the 3 places. The flip side is that 82.8% of the time it was not raining anywhere. Okay, and again, we can use this to compute any probabilities that we might be interested in, such as it was raining in John Day, but it was not raining in Coos Bay, and it was raining in Corvallis, for example. So it was raining in Coos Bay, but not in Corvallis, it was raining in Coos Bay, not in Corvallis, but it was in John Day. That was very confusing, but hopefully you got it. That just happened 0.34% of the time, so not very often. Okay, and we can aggregate them to compute whatever probability we're interested in about these 3 weather stations. Okay, so what have we learned? We have learned the mathematical characterization of joint distributions. We have defined the joint PMF, which is really what we use to describe the joint behavior of discrete random variables, or the discrete uncertain quantities that we use random variables to model. And finally, we have seen how to estimate the joint PMF from data. Thank you very much.